I can't believe this is the last class. I'm so ready for that final exam.
I actually feel pretty good about it.
You always do. But
Right.
seriously, if there's one piece of advice I'd give everyone out there, it's to start that coding exam early. Don't wait until the last minute like I always do.
Solid advice. All right, let's jump into this final deep dive. We're tackling neural networks. And you know what's funny? You've already been using the core concepts without even realizing it. Think back to linear and polynomial regression.
Okay, yeah. Finding the best fit lines and curves for our data. Good times.
Exactly. Both regression and neural networks are all about finding a function that maps inputs to outputs. The difference is that neural networks use a more complex function, one with a structure inspired by, you guessed it, the human brain.
So instead of a simple line, we've got a whole brain-like network doing the mapping. That's wild.
It is pretty wild. And the most basic form of the structure is called a multi-layer perceptron, or MLP. It's basically a network of interconnected nodes organized in layers. You can picture it like those diagrams with circles and lines connecting them.
Oh, I've definitely seen those diagrams. They're everywhere.
Right. You have an input layer where the data goes in one or more hidden layers where the magic happens, and then an output layer that spits out a prediction. And the size of these layers plays a key role.
So like the more nodes in a layer, the more complex the network.
You got it. The number of nodes in the hidden layers is called the width of the network, and the number of hidden layers is the depth. Both width and depth affect the complexity of the function the network can represent. A wider and deeper network can handle more complex patterns in the data, just like a city with more roads and intersections can handle more traffic flow.
Okay, I'm getting the big picture now.
Mm-hmm.
But what's happening inside those layers? How does the data actually flow through them?
Great question. Within each layer, data is transformed in two main steps. First, you have the pre-activation, which is just a weighted sum of the inputs to a node. Think of it like assigning importance to each incoming signal based on its weight. Then we apply something called an activation function to this sum, which gives us the post-activation value.
Weight activation function. Didn't we touch on that with regression?
We did, but they're even more important in neural networks. These functions introduce nonlinearity, allowing the network to model those curvy, complex relationships in the data. There are a bunch of them, linear sigmoid-ton, but the one we'll focus on here is ReLU, which stands for Rectified Linear Unit. It's kind of the star of the show in neural networks these days.
So ReLU is like the go-to activation function. Any reason why it's so popular?
It's popular because it's actually pretty simple and efficient. Plus, it helps solve a pesky problem called vanishing gradients, which can make training deep networks really slow. You can think of it like this ReLU keeps the important signals strong while filtering out the noise.
I see. So it's all about efficiency and getting rid of distractions. Makes sense. But can we see this all in action? I always learn best with a concrete example.
Absolutely. Let's imagine a simple network with two input nodes, one hidden layer with 3 nodes, and a single output node.
Okay, got it. 2 inputs, 3 hidden, 1 output. Picture it.
Now say we feed this network an input vector of 2, 1. Each connection between nodes has a weight associated with it. Let's say the weight connecting the first input to the first hidden node is 1, and the weight connecting the second input to the first hidden node is 2, and so on.
So we're multiplying the input values by these weights?
Exactly. To calculate the pre-activation for the first hidden node, we do 2, 1 plus 1, 2, which equals 4. Then we apply the ReLU activation function. Remember, ReLU just outputs the value itself for positive numbers. So the post-activation for that first hidden node is also 4.
All right, so far so good. We do the same thing for all the other hidden nodes, right?
You got it. And for the output node, we take a weighted sum of the post-activation values from the hidden layer. But typically there's no activation function on the output layer.
So the output layer is like our final answer, kind of like in traditional regression.
Precisely. But here's the thing. Calculating all these values one by one can get really tedious, especially for large networks. That's where things get a bit more, let's say, mathematically elegant.
Elegant math. I'm intrigued.
Instead of doing individual calculations, we can use matrices to represent all the weights in calculations.
Matrices, like from linear algebra.
That's the one. We can use matrix multiplication to calculate all the pre-activations for an entire layer at once.
Yeah.
This is called vectorization, and it's way faster and more efficient, especially when you're dealing with massive networks.
So it's like batch processing the calculations.
Yeah.
Smart.
Exactly. And to make things even more compact and easy to work with, we can use a special notation to represent the whole process of going from input to output.
I love when things get more compact. What does this notation look like?
It's pretty elegant.
Mm-hmm.
For example, we can represent the output of the first hidden layer as H1 equals ReLU W1TX, where X is our input vector, W1 is the weight matrix for that first layer, and ReLU is applied element-wise to the resulting vector. This notation makes things much easier to work with, especially when you have multiple hidden layers.
So we can stack these layer-to-layer calculations like building blocks.
You got it. But this all leads to a crucial question. How do we actually figure out the best values for all those weights in the network? That's what makes the whole thing tick.
Yeah, that's the million-dollar question.
Yeah.
How do we make those weights work their magic?
Well, finding those optimal weights is where the real learning happens. We need to find the values that minimize the error between the network's predictions and the actual values in our data.
So how do we do that? Is there some secret formula?
There's no secret formula, but there is a powerful technique called gradient descent. Remember that from our regression deep dive.
Oh, yeah. It's like that iterative process where we keep adjusting things until we get closer to the best solution.
Exactly. We start with some initial weights, usually random, and then we use gradient descent to iteratively adjust them in the direction that reduces the error.
Okay, that makes sense.
Yeah.
But how do we actually know which direction to adjust the weights in? Do we just guess and check?
Not quite. It would take forever. We need a way to measure how much each weight is contributing to the error. And that's where derivatives come in. Remember those from calculus?
Ugh, calculus. It's coming back to haunt me.
I know. But trust me, derivatives are super helpful here. They tell us how much the error changes when we tweak each weight just a tiny bit.
Okay, so derivatives help us pinpoint the troublemaker weights that are causing the most error.
You got it. And to calculate these derivatives efficiently, we use a technique called backpropagation.
Backpropagation. That sounds intense.
It can be, but the idea is actually pretty intuitive. We calculate those derivatives backward through the network, starting from the output layer and going back to the input. Think of it like unraveling a chain to see how each link contributes to the final outcome.
So it's like we're tracing back the error through the network to see which weights need to be adjusted and by how much.
Precisely. And the chain rule from calculus gives us the mathematical tools to break down these calculations step by step.
This is all starting to click. It's like a detective story where we're tracking down the culprit weights that are throwing things off.
I love that analogy. And just like in a good detective story, the more layers you have, the more complex the investigation becomes, especially with those giant deep networks that have tons of hidden layers.
Speaking of deep networks, you mentioned earlier that training them can get computationally expensive. How expensive are we talking?
Well, imagine a network with millions or even billions of weights. Calculating all those derivatives and updating the weights over and over again can take a massive amount of computing power.
Wow, no wonder people are so excited about the idea of finding those closed-form solutions like the research from Professor Wu.
It would be a game changer. But even with gradient descent and backpropagation, neural networks are already doing incredible things. Think about image recognition, natural language processing, self-driving cars. It's mind-blowing.
It really is, and it all boils down to these surprisingly simple mathematical operations. Who knew matrices and calculus could be so powerful?
That's the beauty of it. From simple building blocks, we can create systems that can learn and make intelligent decisions.
Okay, I'm feeling inspired. But before I get carried away dreaming about AI, maybe we could walk through a simple example to really solidify my understanding. Help me ace that coding exam.
Of course. Let's look at a network with 3 input dimensions, 1 hidden layer with 2 nodes and 1 output dimension.
Okay, I'm picturing it. 3 input nodes feeding into 2 hidden nodes, and then those connect to a single output node.
Exactly. Now notice the weights on each connection. For example, the weight connecting the first input to the first hidden node is 0, 0. The weight connecting the second input to the first hidden node is 2, and so on. These are the W1 values, the weights for the first layer.
Got it. And we can represent those in matrix form, right?
Exactly. In this case, it would be 0, 1, 2, 3, tiras 1, dot 1.
Okay. I see how that maps to the diagram. And the weights for the second layer, W2, would be 1, 2.
Perfect. Now let's say our input vector X is 3 to 0.
All right, so how do we calculate the final output of the network for this specific input?
First, we need to calculate the pre-activation for the hidden layer. We do that by multiplying the input vector X by the transpose of the weight matrix W1.
So that would be 0, 2, then 1, 3, 4. 1, 2, 3, third one, 3. 3 to 1 by 2 equals 9.
You nailed it. Now we apply the ReLU activation function to that result, which gives us 4, 9.
And those are the post-activation values for our hidden layer. What happens next?
Now we calculate the final output by multiplying that result by the weight matrix for the second layer, W2.
Right, so that's 14222 by 9 exactly.
So the output of the network for this input is 22. You just did a forward pass through a neural network.
Wow, that wasn't so bad. I'm starting to feel more confident about this.
That's great to hear. Now just imagine doing this for millions of data points and then using backpropagation to tweak those weights to minimize the error. That's the essence of neural network training.
So it's all starting to come together. Find the right weights, minimize the error, make those predictions.
You got it. And while the math can get complex, the underlying ideas are surprisingly intuitive. It's all about learning from the data. It's wild to think that for so long, a closed-form solution for neural networks seemed like a total pipe dream, like it was this holy grail of AI research. Everyone knew how big of a deal it would be, but no one could crack it.
And then Professor Wu shows up and changes the game.
Pretty much. His research suggests that it might actually be possible to get these closed-form solutions for both regression and classification problems.
That's huge, right? It would make training these massive networks so much faster and more efficient.
For sure. Imagine training a giant neural network in way less time using less energy. It would be revolutionary.
It would be like a cheat code for AI superpowers. But hold on. What exactly is a closed-form solution? Is it some kind of magic formula?
Not magic, but kind of close. Remember in traditional regression, we had that neat equation to just calculate the optimal weights. You know, the one with all the matrices and inverses.
Yeah, vaguely. Good times.
Well, a closed-form solution basically means we have a direct mathematical expression to get the solution without needing those iterative methods like gradient descent.
So did Professor Wu find like a similar equation for neural networks?
It's more complicated than that. Neural networks are inherently nonlinear, which makes finding these closed-form solutions really tough. But Professor Wu's work, based on something called the Wu-Masumi theorem, shows that it might be possible to find solutions that skip gradient descent under certain conditions.
So it's not a one-size-fits-all solution, but it's still a major breakthrough.
Totally. It has the potential to completely change how we think about and use neural networks down the line.
This has been an awesome final deep dive. I feel like my neural network knowledge has leveled up for sure.
Me too.
I am ready for that exam.